You know that feeling? Like information overload. Your brain just feels jammed, signals all tangled up, data looking like a complete mess. But what if, right? What if you had this, like, mathematical superpower, kind of secret decoder that could just untangle it all, reveal the pure, simple bits hidden inside?
It does sound a bit like science fiction, doesn't it?
Yeah,
But that superpower, it actually exists. It's called the Fourier transform.
Fourier transform.
Yeah.
Okay. Sounds a bit intimidating, like something off a physics blackboard.
Yeah, it can sound that way.
Right.
But honestly, it's not some scary abstract thing. It's actually a surprisingly elegant idea.
Wow.
And it pops up everywhere.
Everywhere.
Oh, yeah. Way beyond just sound and frequency. You find it in all sorts of areas of science, engineering,
Hmm.
areas that seem totally unrelated at first glance.
Oh, okay.
So our mission really in this deep dive is to give you a clear introduction, to kind of demystify it, show you how it works, and just how incredibly useful this one single concept is.
A shortcut to sounding smart about signal analysis.
Huh, well, maybe. Consider it a shortcut to being genuinely well-informed on, honestly, one of the most transformative ideas out there.
Okay, let's unpack this then. Let's start with sound. That seems like a good place.
Perfect. So imagine a really simple, pure sound, like the note A. That's 440 vibrations, or beats, per second.
Right.
If you could see the air pressure change, it would be
Wow.
this nice, clean, smooth wave going up and down. Predictable.
And a lower note, like a D.
Same idea. Just, fewer waves per second, slower oscillation. Still pretty straightforward.
Okay. Simple enough. One note, one clean wave.
Exactly. But what happens when you play both notes, the A and the D, at the exact same time?
Ah, okay. Things get messy.
They do. The air pressure graph, it's not that neat wave anymore. At any single
Uh-huh.
moment, the pressure is just the sum of what the A would be doing plus what the D would be doing.
Just sometimes they add up, sometimes they cancel out a bit.
Precisely. Peaks might line up, making it louder. Or
Okay.
a peak might meet a valley, and they sort of counteract each other. The result is this. Well, it's still wave-ish, but it's definitely not a pure, simple wave. It gets, as the source material puts it, kind of a complicated thing to think about.
Right. And I guess if you add more notes or like background static or something.
It just gets worse,
Mm.
more and more tangled. It can start to feel, needlessly complicated when you think about the simple notes you actually put in.
Because your ear, or a microphone, it doesn't hear the separate A and D waves, does it? It just gets the combined result.
Exactly. It only registers that final jumbled sum.
Yeah.
So that brings us to the core problem, the real challenge here.
Which is?
How do you take this messy-looking signal, this complicated sum, and figure out which pure frequencies actually made it up in the first place?
It's like someone mixed blue and yellow paint together to make green, and now you want to get the pure blue and pure yellow back out again?
That's a great analogy, yeah.
Uh-huh.
Pulling them back apart feels exactly like trying to unmix paint. Seems almost impossible.
Oh, some kind of trick, yeah.
And what's fascinating is our ears, they do this separation automatically,
Mm.
effortlessly, but mathematically. Those sounds just merge into this complex mush.
So we need that mathematical trick, that unmixing machine.
Precisely. We need to build a conceptual mathematical machine. And its main strategy has to be treating signals of one specific frequency differently than it treats all the others. It
Yeah.
needs to pick them out.
Okay, how does it do that? This sounds interesting.
This is where it gets really clever and maybe a little abstract visually, but stick with it. The core idea is you take your signal graph, that wiggly line over time,
Yeah.
and you sort of wrap it up around a circle.
Wrap it around a circle. How does that work?
Okay, imagine you have like a little spinning arrow or a vector starting from the center of a circle. At every point in time on your signal graph, you look at the height, the value of the signal. The length of your little rotating arrow at that exact moment is set by that height. So if the signal is high, the arrow stretches further out from the center. If the signal is low or negative, it shrinks closer in, maybe even points the other way.
Huh. So the timeline gets turned into a spiral or some kind of pattern around the circle.
Exactly. It's like transforming that linear time into this dynamic rotating picture.
Okay, I'm picturing it. It sounds potentially complicated.
It can look complicated, yeah.
Yeah.
But here's the crucial bit. There are actually two different frequencies involved now.
Two?
Yeah. First, you have the frequency that might be in your original signal. Like if you play that A note, there's a 440 beats per second frequency in there.
Right, the sound itself.
And then, totally separate, there's the frequency of how fast we choose to wrap the graph around the circle. Let's call that the winding frequency. And we can change that. We can wind it slowly or really fast.
Ah, okay. So one frequency is baked into the signal, the other is a dial we can turn on our wrapping machine.
You got it. And yet the diagrams you get when you do this wrapping could look pretty complicated, but sometimes they're also very pretty. But always remember, fundamentally, all that's happening here is that we're wrapping the signal around a circle. We're just changing its representation.
Okay. So we wrap the signal around a circle at a speed we choose. Why? What does that do?
This is where the magic starts. You get this feeling, this intuition, that something kind of special ought to happen if the speed we choose for wrapping our winding frequency perfectly matches a frequency that's actually in the signal.
Like if the signal has a strong 3 beats per second rhythm, and we set our winding speed to exactly 3 cycles per second.
Exactly that. When those two match, something amazing happens in that wrapped-up picture. All the high points from the original signal, they consistently land on one side of the circle, let's say the right side, and all the low points, they all gather on the opposite side, the left.
Whoa, okay. So it like sorts itself out.
It does. It's this beautiful alignment that only happens when the winding frequency hits a frequency present in the signal.
That's the trick. That's how the machine tells things apart.
That's the core mechanism.
Yeah.
Now, take it one step further. Imagine that wound-up shape, that pattern on the circle.
Hmm?
Imagine it has some mass, like it's a bent piece of metal wire.
Okay, like a physical object now.
Yeah. And what we're interested in is its center of mass, the balancing point of that shape.
Right.
Now, for most winding frequencies, when the signal is wrapped up, the high points and low points are probably scattered all over the place, more or less evenly.
So the center of mass would be near the middle.
Pretty much. It might kind of wobble around a bit, but
Okay.
it stays pretty close to the origin, the center of the circle. It's all averaged out.
What about when the frequencies match? When everything lines up on the right and left?
That's the aha moment. Because all the heavy bits, the high points are on the right, and the light bits, low points are on the left, the overall center of mass gets pulled way over. It's unusually far to the right.
It jumps out.
It jumps out. It's like that hidden frequency is suddenly making its presence known, physically shifting the balance point.
Okay, that's cool. So what do we do with that?
We track it. For every possible winding frequency, we try slow, medium, fast. We calculate where that center of mass lands. Specifically, we can just plot its horizontal position, its x-coordinate.
And what does that plot look like?
You get a graph.
Mm.
And on this graph, you'll see a big, sharp spike right at the winding frequency that matched the frequency in your original signal. For our example, a spike at 3 cycles per second.
So the graph pinpoints the hidden frequencies.
Exactly. Oh, and sometimes you might see a big spike around 0 frequency. That just means your original signal had an overall average value that wasn't 0, like it was shifted upwards. It doesn't represent an oscillation, just a constant offset.
Gotcha. So this graph, the plot of the center of mass's x-coordinate versus winding frequency, that's the Fourier transform.
It's almost the Fourier transform. We call it that in the source, kind of informally. It captures the main idea, just a tiny stick away from the real deal. But this center of mass idea, that's the heart of it. It's the indicator. It's how we find the hidden stuff.
And does this work if there's more than one frequency in the original signal? Like our A and D notes played together?
Yes. This is where the machine becomes really delightful. Let's take that combined signal, the sum of, say, a 2 beats per second wave and a 3 beats per second wave. It looks more complicated, right?
Yeah, that jumbled mess.
Now feed that into our winding machine. As you slowly increase the winding frequency, wrap that complex shape around the circle. Yeah, it looks pretty chaotic most of the time. Just a tangled mess.
Chaos.
Chaos and chaos and chaos and chaos and chaos, as the source vividly puts it. But then, whoop! Suddenly, things seem to line up really nicely when your winding frequency hits 2 cycles per second. The center of mass jumps out to the side.
Spike number 1.
Spike number 1. Then you keep increasing the winding frequency. More chaos, more tangles. Chaos and chaos and chaos and chaos until whoop, things nicely align again when you hit 3 cycles per second. Center of mass jumps out again.
Spike number 2. It found both frequencies.
It's on both. It's almost funny how well it works. That visual chaos resolves into perfect clarity at just the right moments. We've gone from the jumbled sum back to a clear readout showing peaks at 2 hertz and 3 hertz. We found the ingredients. We unmixed the paint.
Okay, why does it work so well with multiple frequencies? Is there a reason it separates them so cleanly?
Yes, there's a fundamental mathematical reason called linearity. It sounds technical, but the idea is simple. Lay it on me. Okay. Imagine you take the 2 hertz signal, find its almost Fourier transform, that center of mass plot with a spike at 2 hertz. Then you do the same for the 3 hertz signal, getting its transform, spike at 3 hertz. Now, add those 2 transform graphs together.
Okay, so I'd have a graph with a spike at 2 and a spike at 3.
Exactly. Now, linearity means you get the exact same result if you first add the 2 hertz and 3 hertz signals together, making the complex wave, and then calculate the transform of that combined wave.
Whoa, so transforming separately and adding is the same as adding first and then transforming.
That's linearity.
Yeah.
And it's super powerful because we know the transform of a single pure frequency is basically 0 everywhere except for that one spike.
Right.
It means the transform of a sum of pure frequencies is just the sum of their individual transforms. You just get this clean graph with little peaks sitting right above the frequencies that went into the original mix.
So the machine really does just perfectly pull out the original frequencies from the jumble. The paint unmixing works?
It works beautifully. It does exactly what we wanted.
Okay, this is clearly powerful for analyzing sound, but you said it goes beyond sound.
Oh, absolutely. This isn't just about audio. The same core idea, breaking down a complex signal or pattern into its fundamental frequencies or components, is used everywhere. Think about JPEG image compression.
How you shrink photos down.
Yeah. Part of how that works involves a 2D version of the Fourier transform. It breaks the image down into different spatial frequencies, like broad areas of color versus fine details. Then it can sort of throw away some of the less important frequency information to save space.
Huh. So it's finding the frequencies of patterns in a picture.
In a way, yes. Or think about medical imaging, like MRI scans. Those machines measure signals from your body, and they use transforms very similar to the Fourier transform to turn that raw data into the detailed images doctors look at. It's about converting signals measured over time or space into a frequency representation that makes sense visually.
Wow. Okay. Seismology, quantum mechanics. You're saying this idea is fundamental.
It really is. It's one of the essential tools for analyzing patterns and signals in so many fields.
Can we look at one practical example, maybe back with sound, like getting rid of noise?
Good idea. Yeah, sound editing is a perfect example. Let's say you have a recording maybe of speech, but there's this annoying high-pitched whine in the background.
Okay, happens all the time.
Right. So your original recording is just sound intensity changing over time. Now you apply the Fourier transform. What do you expect to see on that frequency graph?
Well, I'd see the frequencies that make up the speech, presumably. And that annoying whine would show up as a sharp spike at whatever high frequency it is.
Exactly. It stands out clear as day on the frequency plot.
Mm-hmm.
So if you want to filter it out, what do?
You just erase that spike, or maybe just squash it down.
Precisely. You digitally manipulate the transform graph. You find the spike corresponding to the whine, and you just reduce its height, effectively smushing the spike down.
Okay, so now I have a modified frequency recipe without the annoying ingredient, but that's not sound, that's still a graph.
Right, and this is where the symmetry comes in. There's also something called the inverse Fourier transform.
The way back.
The way back.
Yeah.
It takes your modified frequency graph, the one with the whine removed, and it tells you exactly which time domain signal would produce that specific frequency fingerprint.
So it reconstructs the sound, but without the whine.
Bingo. You transform to the frequency domain, do your editing there, like removing noise, and then you transform back to the time domain to get your clean audio signal. It's like unmixing the paint, removing the bad color, and then perfectly mixing the rest back together.
That's incredibly elegant.
It is. Now, the source does add a little note here saying calling it a perfect inverse is a little bit of a lie, but it's in the direction of truth. There are mathematical subtleties, especially with finite signals, but for intuition, thinking of it as going back and forth between time and frequency is spot on.
Okay, makes sense. Now, you mentioned earlier that the x-coordinate of the center of mass was only almost the Fourier transform. What's the rest of the story?
Right. Good catch.
Yeah.
That center of mass, it's a point in a 2D plane, isn't it? It doesn't just have an x-coordinate left-right. It also has a y-coordinate up-down.
Oh, okay. So we've only been looking at half the information.
Essentially, yes.
Yeah.
And in mathematics, whenever you're dealing with something two-dimensional like that, it's often really elegant and powerful to think about it using the complex plane.
Complex numbers, like with I, the square root of -1.
That's the ones. Don't let the name scare you. They're just a way of handling two-dimensional quantities. Our center of mass point can be represented as a single complex number, which has a real part, the x-coordinate, and an imaginary part, y-coordinate.
Why bother with complex numbers? Why not just keep track of x and y separately?
Because complex numbers are perfect for describing things involving rotation and winding. There's this incredibly beautiful and famous bit of math called Euler's formula.
I think I've heard of that. E to the I times something.
That's the one. E raised to the power of I times some number, let's say x, EIX, geometrically describes moving x units around a circle of radius 1, starting from the right side. It's like a mathematical command for rotate. So if we want to describe rotating at a specific frequency, say f cycles per second, we can use a slightly modified version of this Euler's formula. It looks like e to the power of -2 pi IFT. The t is time, f is our winding frequency. The minus sign is just a convention used in the standard definition of the Fourier transform. It means we wrap clockwise instead of counterclockwise.
Whoa, okay. That expression looks dense.
Yeah.
E to pi IFT. A bit dizzying.
It can look a little dizzying, absolutely. But the amazing thing is that one tiny expression perfectly captures the idea of smoothly rotating around a circle at a frequency f.
The winding part of our machine.
Exactly. Now, remember how the length of our rotating vector was set by the height of our original signal? Let's call it gf.
Yeah.
We can combine these. If you multiply the signal gt by that rotational term e2 pi ift, that combined expression ga8 pi ift, mathematically represents drawing that entire wound-up version of the graph at a specific winding frequency f. It's an incredibly awesome and compact way to write down that whole visualization we built up.
Okay, so that formula basically is the wound-up graph in math language. Now, how do we get the center of mass from that? You mentioned integrals.
Right, so think about finding an average or a center of mass. If you just had a few points, you'd add them up and divide by the number of points, right?
Yeah.
An integral is basically the way mathematicians do that same thing, summing up and averaging, but over a continuous range, like our time interval. So the integral of that complex expression, GFT E2 pi IFT, over our time interval, and then divided by the length of the interval, that gives us the complex number representing the center of mass.
So the integral is just a fancy way of finding the average position, the balance point of that continuously wound-up graph.
Precisely. Even if the calculus looks scary out of context, the underlying meaning is just that, finding the center of mass of the wound-up signal. The whole expression is just the center of mass of the wound-up graph.
Yeah.
No calculus knowledge needed to grasp the core idea.
Okay. We have the wound-up graph formula. We have the integral as the center of mass. Are we there yet? Is that the Fourier transform?
Almost. Just one tiny final step. The actual honest-to-goodness Fourier transform is defined by doing that integral, but you don't divide by the time interval at the end.
Huh. Why leave that out? What does that change?
Well, instead of getting the average position, the center of mass, you get a result that's scaled up. If your signal lasted for 5 seconds, the Fourier transform value would be 5 times bigger than the center of mass value. If it lasted 10 seconds, it'd be 10 times bigger.
So longer signals give bigger results in the transform.
Exactly. It makes intuitive sense, right? If a certain frequency is present in your signal and it persists for a really long time, it contributes more strongly. So, when a certain frequency persists for a long time, then the magnitude of the Fourier transform at that frequency is scaled up more and more. It rewards signals that are strong and sustained.
Okay, that makes sense. So let's recap the whole thing then, the actual Fourier transform.
Right, so you start with your signal, gt, which depends on time. The Fourier transform, often called g-hot, is a new function. Its input isn't time anymore, its input is frequency, f, or winding frequency.
And its output.
Its output for any given frequency f is a complex number. That complex number tells you about the strength, the phase, like the starting position, of that specific frequency f within your original signal gt. That complex number is found by that integral process, which intuitively represents the scaled-up center of mass of the signal wound around a circle at frequency f.
So even though the final formula with the integral and the e to the I stuff looks complicated.
Yeah, it can look daunting, definitely.
If you understand the pieces, the rotation with Euler's formula, multiplying by the signal to get the wound-up shape, and the integral as a kind of center of mass calculation, then it actually makes sense.
Exactly. You can see how this whole thing carries with it a very rich, intuitive meaning. It's not just symbols. It represents that whole process we visualized. Oh, and technically, the purest form often involves integrating from -infinity to infinity, essentially looking at the signal over all possible time. But the core idea is the same.
Wow, okay. We went from jumbled signals and unmixing paint to complex numbers and integrals finding a center of mass.
We did, and it all connects. The Fourier transform gives us this powerful shift in perspective. From the messy time domain to the clean, organized frequency domain. It makes the invisible components audible or visible or just. understandable. It's really a beautiful piece of mathematical intuition made practical.
Man, oh man. Yeah, there's clearly so much depth here. We've really only scratched the surface, haven't we? But it feels like we've seen the core magic, how this seemingly complicated math can be built from these understandable, almost playful ideas like wrapping and balancing.
Definitely.
It's a good reminder, that even complex formulas can hide real beauty and obviously a ton of practical power, turning that chaos into clarity.
And that brings up a final thought, maybe for you, our listener. We've talked a lot about this unmixing paint idea, decomposing complex signals into simpler frequencies.
Right.
So the question is, now that you've seen how this works for signals, where else might this kind of thinking apply? This idea of breaking down complexity, finding the hidden fundamental components. Where else could you use that?
Hmm. Like looking for the underlying frequencies in, I don't know, economic data or social trends, or even just trying to understand a messy problem in your own life by breaking it down.
Perhaps. Keep an eye out for those hidden patterns, the subtle frequencies beneath the surface noise. Once you know how to look, you might find they're really everywhere.
Okay, so there's a human in the loop, just in case you're wondering. Everything we do is available on BioniChaos.com. Go check the website out. Let me know if there's any feedback. Don't forget to like, subscribe, unsubscribe, whatever you have to do. And check Patreon as well if you want to support this project. Whew, that's normally what a robot should say, but so we got this idea from another YouTuber. You probably can guess who that is. Can probably guess, because if you type Fourier transform into YouTube or Google, so it comes up with this video from 3 blue 1 brown. Yeah, that's from 7 years ago. 11 million views. So they have this user interface on the YouTube channel, on the video. I'm not sure what software. Supposedly they have their own software that they use, and we actually making a version of that just available in your web browser, because I don't think it's currently available. So surely after 7 years, and yeah, we obviously using Gemini for that, so I might actually need a that's the original video. Go check it out. So it has this a user interface in it, which we are trying to replicate in the web application. Check out the video, and we have Gemini doing that for us. Okay, we're having a few issues. Okay, so there's a couple of things. First of all, on smaller, wider screen, all the three charts do not fit onto the screen, so only get the one. I can do. I'll share a image with you of how it looks like. Maybe you can fix it so all the canvas, all the components of the canvas are visible properly. Surely it's a simple fix. Now also, if we can, the auto demo mode working really well, so love that. Keep everything else as is, but perhaps just one thing, maybe we can add a few more examples of different waveforms. Anything you can come up with to let me know. I'm thinking 3 different frequency components. but it should fit within the frequency range we are currently working with. And anything else you can think of, go for it. And you can update the canvas directly. Yeah, because we have a version of this running locally on our server. And as I said before, everything we do is available on BioniChaos.com. Go check out that website. See if there's any questions. If you have any questions, if you are human, and you have any questions. So what's happening with the stream? It's not being promoted by the algorithm. Fortunately or fortunately, I don't know. Maybe you don't want it to be promoted. Might also bring in a prompt engineer. Hey, can we preset some sort of proportions for the user interface and keep them the same regardless of what the screen size is? Because currently I have to scroll to see, I have to scroll to see the whole user interface of the simulation game web application. Hey, can we update the code in the canvas? Can we update the code in the canvas directly? Let's actually let's bring a prompt engineer. So using Gemini, share the screen, share the developer. Hey, can you tell me what's currently happening on the screen? What's the developer doing at the moment?
The developer is working on some CSS code, specifically adjusting the layout for a website. They seem to be focusing on making the design responsive, using flexible box properties and viewport units so that the elements fits well on different screen sizes.
Okay, and looking at the code, real quick. What do you think yeah, we can have the application. So yeah, so we're having this issue with the screen. So we don't see all the elements at the same time. Can you explain it properly? What's going on? There's another two charts that meant to be viewable. Yeah, if I increase the zoom, reduce the zoom, then you get this two have screens that are not properly visible. Can you explain it properly? What's going on?
From what I see, the issue is that the layout isn't properly adjusting to different screen sizes. When the screen is smaller or the zoom is reduced, some of the charts are not fully visible, and you might need to scroll to see them. The developer is trying to fix this by using flexible layout techniques to ensure that all the elements remain visible without needing to scroll, regardless of the screen size.
Okay, on the left side there you have the text. That's the thinking process from the developer. Can you go over that? Tell me what is it they're doing?
Sure. The developer is explaining their thought process. They acknowledge the issue with the layout not fitting smaller screens and mention they've updated the CSS to use flexible box properties and viewport units. This should ensure that all the charts and controls are visible without scrolling, adapting to different screen sizes.
Yeah, but that still doesn't work unless I zoom out. I see the other charts, otherwise I don't see them. It should work in 100% zoom.
I understand. It seems the layout adjustments might not be working as expected at 100% zoom, preventing all the charts from being visible. The developer mentioned they were validating the layout, so there might still be some issues to resolve with the responsiveness on different screen sizes.
Okay, can you go over the developer's thinking process?
The developer is examining the layout fix they implemented. They realize that it hasn't fully resolved the visibility issue, especially.
Yeah, keep going.
Okay, they suspect the problem might be with how the body's flex properties are interacting with the chart's dimensions.
Okay, keep going.
They are now focusing on ensuring that the chart's container doesn't overflow at any zoom level. The user's feedback highlighted this persistent visibility issue, leading them to take a deeper dive into the CSS layout. They are implementing further adjustments, like reducing margins and padding, and using a responsive font size for the title to optimize vertical space and ensure all components are visible without scrolling.
Okay, and they're updating the code at the moment, but can you go over, this must be a styling issue. Can you go over the styling real quick? Let me know if you see anything that might be causing issues, potentially.
Yes, the developer is refining the CSS. They've reduced the vertical margins and paddings around the main simulation area.
Okay, it's actually seemed to work now.
Great! It sounds like the refined CSS adjustments have fixed the layout issue. All the charts and controls should.
Oops. Wait, by mistake, dropped the call with the prompt engineer. Oops, a daisy. Let's deploy this quickly. Potentially get back to the prompt engineer again for them to explain what's going on. Okay, there's still something weird. Seem to be having the same problem. Can we check the entire code again? Let's try calling the prompt engineer again. Can you tell me what's happening on the screen real quick?
It looks like you're viewing a simulation of a Fourier series explorer. It's visualizing different waveforms being created by combining sine waves, and you can see the center of mass indicated on the graph.
I'm zooming out now from 100% to 90, 80, 60, 50 at the 33% zoom level. The web application actually looks like how it meant to look like. Can you explain what the problem might be? Why at the 100% zoom I'm not able to see all the components?
It seems the layout isn't adjusting properly.
Yeah, keep going.
Isn't adjusting properly at 100% zoom, causing some parts to be cut off and require scrolling. It seems the fixed sizes of the charts and controls are not fitting within the available space at that zoom level.
Yeah, so I have this experienced developer actually writing this code, but they seem to be having trouble. Any funny comments on that?
Well, it does seem like the developer is facing some challenges with the layout fitting correctly, especially when zooming. It's a common issue in web development, so they're definitely not alone in encountering this. It just means the responsive design needs a bit more tweaking.
Okay, what's the developer doing at the moment?
The developer is currently examining the CSS and looking at how the HTML elements are laid out to figure out why the layout isn't adjusting properly.
Yeah, keep going.
They're looking into adjusting the CSS to use percentage-based sizing and viewport units instead of fixed sizes to make the layout more responsive and fit different screen sizes.
Okay, keep going. What else?
They've also decided to remove the JavaScript function that was previously handling the layout and rely more on the CSS Flexbox for a more robust solution. They're testing different zoom levels to make sure the layout works correctly.
Okay, it seemed to be really struggling. So still same problem at the 33% zoom level. I can see all the simulation web application canvas correctly as I want it to be, but at 100% I only see half of the top graph. So can you explain properly what's going on?
It seems the layout isn't adjusting properly when you zoom in to 100%.
Yeah, keep going. Keep going. Keep going. Keep going. We lost. We lose the prompt engineer again. Ba-ba. It's frustrating. It's all the issues are whatever the last mile type of problems. Okay, did you update the code? We're still having the same trouble that at the 100% view, we only see half of the top chart, and only zooming out to 33% we see the whole canvas properly as we. It's only when we zoom out to 33% of the window size we can see the whole canvas as we want it to be, all the component elements visible properly. So how shall we fix the code? That's distortion, by the way. Okay, we have to fix this layout. This web app looks very promising. Can add some more musical sounding better signals. Actually have robots. Should we engage robots?
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
We have some more of those.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
How do you like that? This is obviously from Sora.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to gently click like, subscribe, and comment.
I think that's the same
Everything
one.
we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
Okay, so we have the code updated by Gemini. Let's see if it's actually... Okay, that's 100% screen size. No. Let's actually have another AI looking at this. Yeah, let's let's do this one real quick. Fix it. Which model should we use? Are we using agent? No. Let's do Claude Sonnet 3.7. Sure. They keep changing how you interact with this thing. In the chat, can you summarize what the problem actually is, standalone, without any code, just text response? So let's get Gemini talking to Claude. Okay, I have a pretty decent summary. Let's give it 3.7 as in an agent mode. Okay, so it got the code. Hopefully it got the correct code. Yeah, Claude seemed to know what it's doing. The senior developer right there. I have to trust the process of vibe coding. And while it's doing the code editing, go check out BioniChaos.com. Everything we do is available on that site. Let me know if you have any questions. And by saying any questions, I mean questions about the content of the website. Yeah, apparently it's something with the screen height that might be problematic. Well, once it fixes anything, well, because the agent's actually editing the code, so we should be able to see if it's working or not. Flex, it's removed the flex growing. Overflow hidden. Change the flex 1. Okay. So it should know what is it doing, I would imagine.
Welcome back to our deep dive. We've got this stack of research in front of us today, all trying to figure out how to find specific kinds of medical data.
Yeah, it's a real hunt. We're looking specifically for publicly available data sets that have raw EEG, ECG, PPG, and imaging data.
All for the same patients, right?
Exactly. And critically, data that you could potentially use to build something like a cardiovascular web application. That's the target.
Okay, so our mission today is to unpack all this research, map out why it's so challenging, and, figure out what's actually out there for you.
And the hook really is, why is this specific mix EEG, ECG, PPG, imaging? Why is that so hard to find together? And what cool things could you unlock if you actually found it?
Let's get into it. The core challenge, reading through these sources, seems pretty clear.
It really is. Finding data sets with all 4 of those raw data types from the same people, plus linkable imaging. That's rare.
And then there's the licensing layer on top.
Right. Finding one where the license actually permits use in something like a web app, potentially commercial, adds a whole other level of difficulty.
Okay, let's clarify raw data first. It sounds like it means different things for different signals.
It definitely does. For sensors like EEG, ECG, PPG, raw usually means the unprocessed high-frequency signals. Think of voltage readings, basically straight off the sensor before much cleanup.
Gotcha. Not just like the heart rate number, but the actual waveform.
Precisely. And for imaging, say MRI or CT, RAW often means the DICOM files. They have the image pixel data plus a ton of metadata.
Okay.
For MRI, you could even go deeper to case-based data, which is the frequency domain stuff before an image is even made. Super fundamental.
And why bother getting all these different types, brain signals, heart signals, images from the same person? What's the big deal with this multimodal approach?
This is where it gets really powerful. Combining these different views gives you a much, much richer picture of someone's health.
More than just looking at one thing in isolation.
Way more. The research strongly suggests this is vital for building smarter AI models that can spot connections, between heart activity, maybe brain responses related to the nervous system, and what you actually see in an image, things you'd completely miss otherwise.
Okay, so it enables potentially more advanced diagnostics or predictions.
Exactly. Think about AI spotting subtle cardiac risks by linking ECG changes with EEG patterns and maybe some structural detail from an MRI. That's the potential.
So let's talk candidates. What data sets did our sources highlight as getting closest to this ideal mix?
Well, the name that comes up constantly is MIMIC-D. It's huge, based on ICU patients, loads of clinical details.
And crucially for us.
It has a waveform module with raw ECG and PPG. Plus, you can link it to the MIMCXR database for chest x-rays. So, strong on the cardio side.
Okay, ECG, PPG, x-rays. Sounds pretty good.
Yeah.
But what's the big gap based on our specific needs here?
The main one, if you need all 4, is that MIMIC doesn't systematically include raw EEG data for these same patients. It's just not routinely collected or included in that part.
Okay. So missing a key piece of our puzzle. And what about access? Is it just download and go?
Oh, definitely not. You need to get credentialed, prove you're a legitimate researcher, and you have to sign a very strict data use agreement, a DUA.
And that DUA limits things.
Significantly, it heavily restricts redistribution and aims to prevent re-identification. That's a major consideration if you're thinking about putting data, even derived data, into a public web app.
Right, that makes sense. So MIMIEC TAFE, great resource, but no EEG and DUA hurdles. What else came up?
Another one mentioned is MCME. It's also on PhysioNet, like MEP. This one's from an emergency department setting.
So different contexts, maybe more acute cases.
Yeah, potentially very relevant for acute heart issues. It includes ECG and PPG waveforms, and it mentions links to imaging results.
Okay, ECG, PPG, but the limitations.
Same issue, no systematic ED data included, and the sources were a bit unclear if imaging results means you get the actual raw image files like DICOMs or just, the radiologist's reports.
I see. So maybe not the raw image data itself.
Licensing probably also requires a DUA, similar process to MIMIC likely.
Okay, so the big ICU and ED data sets are strong on sensors and some imaging link, but consistently miss the raw EG and have these access and use restrictions.
That's the pattern, yeah.
What about places known for specific data types, like just EG or just cardiac MRI?
Good question. The research mentions places like Open Neuro, which is fantastic for EEG data, lots of raw EG.
Okay.
And for specific cardiac imaging, there are things like CMRX Recon, which actually has raw MRI case-based data for the heart, or EchoNet, which has cardiac ultrasound videos.
But the catch is?
The catch is they typically don't have the other pieces for the same people. You get great EEG on OpenNeuro, but not usually their concurrent ECG and PPG. You get amazing cardiac images, but maybe not the simultaneous sensor streams from those exact patients.
So they're siloed by modality, mostly.
Pretty much. And again, licenses can be an issue. ECRNet is often marked research use only. CMRX Recon explicitly prohibits commercial use of the dataset itself. That's often a non-starter for a web application aiming for wider use, potentially.
So, wrapping my head around this, the primary takeaway seems to be that specific combination, raw, EEG, ECG, PPG, plus good cardiovascular imaging, same person, permissive license. That's the unicorn.
That's a good way to put it. Finding that publicly available, ready-to-use package is, based on everything we reviewed, extremely unlikely right now.
So what does this mean for you, the listener, if you're dreaming of building that next-gen cardiovascular web app?
It means you probably can't just download the perfect dataset off the shelf. You'll likely need to make some tough choices.
Like maybe prioritize. Pick the dataset that gets you closest, like AMI Poivi if ECG, PPG, CX are a key, and accept the EEG gap.
Exactly. Or you face the challenge of trying to combine data from different sources, data fusion. The reports mention this, but also highlight that it's technically really, really complex to do well. Matching patients, aligning time series. It's hard.
Okay, so to summarize this deep dive, the landscape for this specific data combination is tough, but maybe not impossible, just complicated.
Yeah, and there is a positive trend towards more data sharing, even complex multimodal data, so things might improve.
But for now, the strategy seems to be pick the best fit you can find, really understand its limits, like that EEG gap we keep mentioning in MEMIAMP or MCMD, and then just scrutinize the license. Every single word.
Absolutely. Read that DUA or license agreement incredibly carefully to ensure your specific web application idea is even allowed.
And don't forget the practical side. These raw data sets are huge.
Oh yeah, terabytes easily. So you need serious storage, serious processing power, good bandwidth. That's a big factor for any web application backend.
Plus the whole ethical and legal responsibility angle. This is sensitive stuff.
Hugely important. Handling patient data means complying with DUAs, yes, but also broader rules like HIPAA in the US or GDPR in Europe, depending on data origin and use. Privacy, security, they're not optional.
Which leads us to a final thought for you to chew on. Given all these hurdles, the access, the privacy rules, the data gaps we found,
what are the biggest ethical questions you would need to really grapple with right from the start before building a public web application using this kind of sensitive, raw, multimodal medical data?
something important to consider as you navigate this space. Thanks for joining our deep dive today.
Welcome to a new deep dive. Today, we're peeling back the layers on something really fascinating, EEG technologies. We were inspired by this interactive guide to EEG technologies. And, well, our mission is to explore how we actually listen in on the brain and maybe understand what these incredible tools can tell us, about ourselves. We'll try to unpack everything from the basics right up to the cutting edge stuff. Looking at the trade-offs, some surprising insights for you along the way.
Absolutely. And, when we talk about listening to the brain's electrical whispers, it really all begins with the electrodes, their design, the material they're made from. It's fundamental. It massively influences the quality of the data we actually capture.
Right. Getting the clearest signal possible.
Exactly. Right from the source.
And to make sure we can actually compare that data reliably between different studies or different people.
That's where the standardized international placement systems come in. They're crucial. They're quite smart, really.
Yeah.
They adapt to individual head measurements, so it ensures consistency. reproducibility, which is vital for research.
But that brings us to a really critical point, doesn't it? Is every method of listening equal? Or are there always big compromises?
That's the core question, really. We often talk about the spectrum of invasiveness,
Mm,
and it highlights this direct trade-off you mentioned.
okay.
The closer an electrode gets to the actual brain tissue, the higher the signal quality you're likely to get. Much cleaner data. But, as you'd expect, that comes at a cost. A clear cost.
Increased surgical risk.
Precisely. Increased risk. And what's really interesting is you see these distinct sort of step-like improvements in the information quality as you increase invasiveness. It's almost like leveling up the detail you can see.
Wow. So if you have these big differences in invasiveness and what you get out of it, how does that actually play out? In the real world, how do doctors weigh those risks?
Well, take a really critical situation like planning epilepsy surgery.
Yeah.
The choice between highly invasive techniques becomes absolutely paramount. So you might be choosing between, say, stereoelectroencephalography, SEEG. That's where tiny electrodes are surgically placed deep inside the brain itself, really trying to pinpoint where seizures start.
Right inside. Okay.
Versus something like subdural grids, SDE. Electrode arrays positioned right on the brain surface. And recent evidence from a large international registry actually directly compares these. It shows some significant differences in their safety profiles and how effective they are diagnostically. It's all about getting the most precise information possible while crucially minimizing risk for the patient.
So beyond the actual hardware, the electrodes and wires, what are these technologies letting us see? What kind of information are we actually picking up?
Yeah, good question. They essentially allow us to visualize dynamic brain rhythms,
Yeah.
different frequencies that we know are associated with different mental states.
Like brainwaves.
Exactly. Brain waves. You can think of them like the brain's different musical notes almost. You have delta waves, those slow, deep rhythms of sleep. Then theta for that sort of drowsy, meditative state. Alpha is that calm, idling hum when you're maybe unfocused but awake. And beta waves, those are the faster frequencies you see with active thinking, concentration. These rhythms, they're really the fundamental building blocks for analyzing EEG data.
Okay, so it sounds like ultimately the choice of which EEG tech to use, it's always driven by the specific goal. You pick the right tool for the job at hand.
Precisely. Yeah, exactly right. Whether it's for precise clinical diagnostics, like we discussed with epilepsy, or cutting-edge neurological research trying to understand brain function, or even, consumer products now. Things like advanced sleep trackers or maybe meditation feedback devices. Different methods, different modalities are tailored for those specific contexts. It's always balancing the detail you need with safety and, practicality. We're even seeing really interesting progress in neurofeedback, helping people learn to regulate their own brain activity.
Right.
And of course, the very experimental work in brain-computer interfaces.
Allowing thought control.
Yeah, potentially. It's early days, but fascinating.
This has been incredibly insightful, really. Thinking about everything from those tiny electrodes just sitting on the scalp, all the way to these complex rhythms mapping our thoughts and these huge decisions made in surgery. It really does show how much we can learn just by, listening in. It absolutely underscores that point. Understanding EEG, choosing the right approach. It's always about balancing signal fidelity, what you want to see, with the practicalities and the risks involved. It's a constant balancing act.
Which I suppose raises a big question for you listening right now. As these EEG technologies keep getting better, more sophisticated, maybe even more integrated into our daily lives, think wearable tech perhaps, or smart environments reacting to our brain states, how might our fundamental understanding of consciousness, of brain function itself, actually shift? What new frontiers could these insights unlock for all of us? Something to think about.
if you were wondering. Trying to fix a few things. Trying to fix this one before making it available for you. I'm trying to have all this audio description on every page for your convenience as well. It seems like I forgot to edit over here. So there's a notebook LM with the descriptions. You can probably hear. It's really funny when I start talking, the views actually drop. But notebook LM gets way more interactions. So what does it mean for humans? What does it mean for humans? Yes, screen sizes is a bit of a pain because it's working really well on one screen, but then not really on another, which is a bit annoying. Okay, let's listen to this one. But yeah, let me know if there's any questions.
Okay, let's unpack this. Today we're taking a deep dive into, well, the really fascinating world of sound and waves. Specifically, how seemingly complex signals are actually built from surprisingly simple components. Our source for this is a look into the interface of something called a Fourier series explorer. It gives us a high-fidelity Fourier simulation. So our mission really is to understand how this explorer visualizes the decomposition of sounds, showing everything from just a basic single 1 Hz wave up to fundamental shapes like square, sawtooth, and triangle waveforms.
Yeah, and what's really great is that the tool doesn't just stop there with the basics. It also brilliantly demonstrates how you create more elaborate things like a complex tone or even a three-tone chord. And it shows that interesting phenomenon of beats, too. It even gives a specific example like combining 2 Hertz plus 3 Hertz. Plus, we'll look at some other intriguing bits like center of mass and controls. You see like 0.00000 cycle second audio, off, and drawing speed. These all offer some, unique ways to understand and even manipulate these basic building blocks of signals.
That sounds like a fantastic roadmap. Okay, so let's start with the absolute fundamentals then. This explorer kicks off by showing us that single 1 Hz wave. What's that basic wave telling us? Why is it so crucial?
Well, what's fascinating is that single 1 Hz wave is just the most basic sine wave you can have. Smooth, repeating oscillation. It's really the simplest ingredient, in the whole recipe of sound. The core idea behind Fourier series, and what this explorer shows so clearly, is that any complex sound wave, doesn't matter how intricate, it can be broken down into a sum of these simple sine waves, each with its own frequency, its own amplitude. It's kind of like taking apart a complex dish back into its individual spices.
Right, I see. So if that's our basic building block, how does the explorer then show us something like a square wave or a sawtooth or triangle? What makes those fundamental, and what do they actually sound like?
Good question. So these waveforms, square, sawtooth, triangle, they're fundamental because they have these distinct, recognizable harmonic structures, meaning they're made up of very specific sets of those sine waves we just talked about.
Okay.
A square wave, for instance, it sounds kind of buzzy, a bit hollow. That's because it's built from an infinite series of odd-numbered harmonics. The explorer actually visualizes adding these odd sine waves one after another. You see how their sum gradually makes that sharp square shape? A sawtooth wave, though, sounds brighter, fuller. Think like a brass instrument. That's because it contains all the integer harmonics. And the triangle wave, that one's softer, maybe more flute-like. It uses only odd harmonics, too, but their amplitudes drop off faster. The simulation lets you literally see these simple signs stacking up. It's pretty cool how they create these complex, distinct shapes and sounds.
Yeah, it really is incredible to visualize that. Okay, so once we get how those fundamental shapes are built, how does the Explorer move on to showing more elaborate things, like a complex tone or that three-tone chord?
Right, so this is where we shift from taking things apart to putting them together, deconstruction to construction. The Explorer takes those individual sine wave components and shows how, by combining them in specific ways, you can build something much richer. A complex tone is essentially just a sound made of multiple sine waves that are harmonically related, meaning they're integer multiples of a base frequency. That gives it a richer timbre than just a plain sine wave.
Uh-huh.
A three-tone chord then just takes it a step further. It combines three distinct frequencies, often chosen to sound, harmonious or maybe dissonant. And the visualization really shows how these individual waves interact, reinforcing here, canceling out there to make the overall shape of the chord.
And what about beats? The source mentioned 2 hertz plus 3 hertz. That sounds simple, but what's happening? What do beats sound like?
Beats are a really interesting auditory effect. They happen when you play two sound waves with just slightly different frequencies together, like with 2 hertz plus 3 hertz. You don't really hear two separate tones. You hear a single combined tone, but its loudness, its amplitude goes up and down rhythmically.
Oh,
The Explorer shows this really well. You see the two separate waves, then you see their sum, and you'll notice the resulting wave's amplitude getting louder and softer periodically. That's the two waves interfering, constructively and destructively. It creates that distinct wah wah wah, or like a throbbing sound. It's actually used a lot when tuning instruments.
that makes sense. It's a perfect example of simple things combining for surprising effects. Now, beyond just showing the waves, this Explorer has some interesting interactive bits, like center of mass. What does that tell us about a signal?
Yeah, the center of mass here is a really clever visual cue. In signal analysis, it sort of helps us understand where the sound's energy is concentrated, or you could think of it as its auditory weight across the different frequencies. If the center of mass is lower, it suggests more energy down low. In the bass frequencies, so heavier sound. If it's higher, more energy's up high. A brighter sound, maybe thinner. It's a quick way to just gauge the overall tonal balance of a complex wave.
And those other controls, like 0.00 cycle second, audio, over, drawing speed, how do they help?
Right. Those controls are actually pretty powerful for digging deeper. Setting 0.000 cycle second, that basically freezes the animation, stops the waves moving. So you can really inspect the waveform at one point in time, see its exact shape, how the components line up without the motion distracting you.
Oh.
Audio OTOF is simple but useful. It lets you just focus purely on the visuals first, which is great for learning. Then turn the sound back on to connect the two.
Yeah.
And drawing speed, that's fantastic. You can slow the whole process right down, see each sine wave component being added step by step, building the complex wave. It really makes that abstract idea of summation feel, well, tangible.
So what does this all really mean for us? I mean, this deep dive into the Fourier series Explorer has really shown quite vividly how the fabric of complex sounds, from a three-tone chord to those intricate beats from 2 hertz plus 3 hertz. It's all elegantly built from basic elements, things like square or triangle waves, and it's all visualized through this high-fidelity Fourier simulation. It's like seeing the simple parts inside the complex whole.
Exactly. And, this raises kind of an important question, I think. Considering how a simulation like this can make the invisible world of frequency and waves so tangible, so understandable. How might understanding these fundamental principles like Fourier analysis, like center of mass in signals, how might that empower us? Could we use similar ideas, this deconstruction approach, to understand other complex systems in our world way beyond just sound? How can breaking something down into its core components help us understand, well, almost anything better?
That's a really powerful thought to end on. Thank you for joining us on this deep dive.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to gently click like, subscribe, and comment. Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
Okay, let's unpack this then. Imagine taking something, well, totally fundamental like walking, and turning it into this interactive science experiment.
Yeah, it sounds a bit strange when you put it like that, doesn't it?
It kind of does. So today we're diving deep into GateSim. It's this really fascinating human biomechanics and movement simulator.
Right, we've got some pretty technical sources on it.
We do. And our mission, really, is to cut through the jargon. We want to show you why, digitally dissecting a simple stroll can actually lead to some pretty surprising insights.
We're talking about the human gait cycle here.
Exactly. That whole sequence, like from when your foot hits the ground to when the same foot hits it again, seeing that whole thing in a new light, maybe even a slightly ironic one.
Definitely some irony there.
So at its heart, GateSim is this sophisticated interactive 3D animation, right?
Yeah, but it's much more than just a visual. It's like a living model of how we move. It's got live metrics pouring out, loads of educational content packed in.
So it brings these really complex biomechanics principles to life, makes them observable.
Precisely. And what really makes GateSim stand out, I think, is that it's built for serious applications. It's not just about cool animations. It's a tool.
A tool for what specifically?
Well, for understanding movement dynamics, both medically and in engineering. Think of it like a virtual lab. You can get into really granular detail on, basic human functions, stuff you just can't see easily with the naked eye in a normal lab.
Right, the subtleties. And the key thing is that you get to play with it. Yeah, the interactive bit.
Absolutely. That's crucial.
You're controlling an avatar, messing with variables, and seeing the impact, like, instantly.
Yep. You're not just watching, you're actively engaging. You might tweak the stride lengths.
How far you step.
Right. Or the cadence.
How fast you step.
Straight from a control panel. And yeah, there's the irony, isn't it? Simulating something so fluid with digital command.
Yeah. But that hands-on part, that's what unlocks the analysis, you figure.
That interactivity is absolutely critical. It lets you visualize cause and effect in real time, like immediately. You see how the avatar deals with obstacles or how its gait changes when you fiddle with a setting?
So it makes abstract ideas really tangible.
Exactly. You might spot how, say, a tiny shift in hip rotation, something you'd never notice otherwise, could actually put a lot of stress on the knee over time.
Wow. An insight you'd only get from this kind of virtual analysis.
Precisely. That instant feedback really accelerates the learning for researchers, for clinicians.
That's fascinating. So, okay, beyond just the interactive fun of it, where is GateSim actually being used? What are the critical applications now?
Well, in medicine, it's proving really invaluable for diagnosing gait issues, tracking recovery, think Parkinson's patients, or stroke rehab.
So it gives objective data to tailor the therapy.
Exactly, much more precision.
Yeah.
And then on the engineering side, maybe designing better prosthetics, or even things like optimizing workspaces, ergonomics, making sure equipment fits how humans actually move efficiently.
Taking that simple stroll and breaking it down into useful data,
That's the idea.
that real-time analysis is powerful.
Yeah.
And this kind of leads us to where it's all going, right? Because if you can dissect a generic stride, imagine personalizing it.
Yeah.
The future stuff sounds genuinely transformative.
Oh, definitely.
They're looking at pulling in real-world biomedical data to simulate individual gait patterns.
Yeah, and that personalization is the real game changer. Simulating someone's specific way of walking opens up so much. Advanced analytics for very specific gait problems, highly customized rehab plans.
So it's not just an avatar, it could be your stride being analyzed.
Potentially, yes.
Yeah.
Which, is incredibly promising for therapy, but also maybe a little unnerving.
Unnerving how?
Well, for those of us who kind of like our natural, perfectly imperfect ways of moving,
Yeah.
it raises questions, about optimizing everything versus just letting things be.
Yeah, good point. Like how much optimization is too much?
Yeah.
When do we start losing what makes our movement, well, human?
It's something to think about.
And it doesn't stop there, does it?
Yeah.
We're talking about adding more environmental stuff like uneven ground, stairs.
Make it even more comprehensive, yeah. And get this. Support for wearable sensors.
Wearable sensors, like my fitness tracker.
Exactly. Feeding data directly into the simulator for real-time feedback and visualization.
So in the future, my watch could tell Gait Sim how I'm walking, and it shows me digitally how I could be better.
That's the direction. It's like having your own personal digital walking coach.
A potentially quite judgmental one about my natural shuffle.
Huh. Could be.
Okay, so we've walked through Gait Sim's digital corridors.
Right.
From the almost playful controls and that ironic interaction to the really serious applications and where it's heading.
Yeah, and what's compelling, I think, is seeing something we think of as totally mundane, like walking, broken down into such precise, measurable data. It just reveals the incredible complexity under every single step.
It really does.
And it forces you to connect it to the bigger picture, maybe. It raises that question. In a world where our most basic movements can be simulated, optimized, maybe even corrected, what does that actually mean for our natural, perfectly imperfect human stride?
Something to definitely ponder on your next walk.
That was Notebook LM, a Gemini Claude making the code. There's a human in the loop. If you have any questions, go for it. Otherwise, everything we do is available on BioniChaos.com. Go check it out, provide your feedback. Don't forget to like, subscribe, unsubscribe. You know what to do.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to gently click like, subscribe, and comment. Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
You have to listen to the robot. Do what the robot said.
Welcome to the deep dive. Today we're venturing into a really fascinating space, exploring excerpts from BioniChaos, interactive biomedical tools and simulators. Our mission for this deep dive is basically to show you how these incredibly complex biomedical concepts can become, well, not just accessible, but surprisingly hands-on and even, like, fun. It's almost funny, isn't it, how engaging something so intricate can actually be?
That's absolutely right. Yeah, it's really about transforming that sort of passive learning into active exploration. It offers you this unique sandbox, to play in for understanding the human body and the technology that interacts with it.
Okay, right. Let's unpack this a bit. Imagine just trying to really get complex physiological data without seeing it move, seeing it react. These BioniChaos tools are not just static dashboards, they're more like dynamic learning environments. We're talking about tools where you can, practically play with brain waves or fine-tune heart rhythms. It sounds wild.
It is pretty wild. And what's fascinating here is how they take this raw, often really intricate data and turn it into these engaging interactive experiences. So for instance, you've got the modality comparison bubble chart. It visually compares different physiological and sensing modalities based on their temporal and spatial resolution.
Okay.
So like speed versus detail and location,
Yeah.
it gives you a great visual starting point.
Right, a baseline. And okay, here's where the simulators really come into their own, I think. We're talking about tools like the Advanced EEG Signal Simulator. Here you can actually customize brain waves, delta, theta, alpha, beta patterns, and you can even simulate artifacts.
Artifacts, yeah, those unwanted interferences,
Right.
super important.
Exactly, for a complete picture.
Precisely. Or you take the ECG simulator. That lets you explore various cardiac rhythms, see the effects of different electrophysiological parameters directly on the ECG waveforms, which it raises a really important question. How does actively simulating these vital signs deepen understanding compared to just, say, reading about them in a textbook?
That really is the core of it, isn't it? It's the interactivity. It gives you that immediate feedback, cause and effect right there. You're not just reading, okay, if X happens, Y occurs. You're making X happen and seeing Y occur, like, instantly. And I think this active experimentation is also why something like the synthetic noise generator dashboard is so valuable. You might just think, oh, noise is noise, right?
Yeah.
But here you can generate and visualize different types, white, pink, brown, even periodic noise, and really understand how they mess with actual signals.
Yeah, and that's crucial because in real-world biomedical data, noise is a huge challenge. So understanding it interactively, that really helps with cleaning data, interpreting it properly. And if we connect this to the bigger picture, it's really about making these abstract concepts tangible. Think about the cochlear implant simulation. You can literally visualize the electrical signals sent to the brain, adjust parameters, see what happens. Plus, there's even an interactive cochlear implant insertion simulator. You can explore the actual mechanics of putting the implant in. It's built using 3.js and chart.js. Pretty neat stuff.
That's incredible. It's almost like having a virtual medical lab right at your fingertips. Honestly, it makes me think back to college, struggling with some of these concepts. If only I'd had a tool like this back then to actually see the changes, Does that hands-on experience really cut down the learning time?
Oh, absolutely. That immediate feedback loop, the direct manipulation, it just accelerates how you build intuition.
Yeah.
Massively. And for people curious about real-world stuff and thinking critically, there's the Epilepsy and Cardiac Health, an interactive evidence review. This lets you dive right into the research, compare, say, anti-epileptic medication effects, look at different study methods.
That's fantastic for getting into actual research data.
Uh-huh.
Oh, and for the real data explorers out there, the Interactive Explorer, public multimodal biomedical data sets. Sounds like a gold mine. Sifting through real EEG, ECG, PPG.
FO and IRS signals.
Right. FNIRS, functional near-infrared spectroscopy, that non-invasive brain activity measure. And from there, you can even explore using advanced analysis machine learning for things like seizure detection with tools like Rhythm Scan.
Exactly. It's not just about passively consuming information anymore. It's about becoming an active participant. You're analyzing, questioning, testing hypotheses, all without needing a physical lab right away. It empowers you.
So wrapping this up, what does it all mean? I think this deep dive into BioniChaos really shows us that understanding complex biomedical engineering It doesn't have to be this like daunting mountain to climb. It can actually be incredibly hands-on, engaging, and yeah, surprisingly fun. It turns potential frustration into real discovery.
Well said. Knowledge is really most valuable when it's understood and applied, right? These tools empower you listening to not just consume information, but to interact with it, to experiment, and to truly grasp the intricacies of our biology and the tech designed to help us understand it.
So here's a final thought for you to ponder. Imagine if all learning could be this interactive. What seemingly impossible medical or scientific challenge might you feel equipped to tackle just by being able to virtually play with the problem and its data? Something to think about.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to gently click like, subscribe, and comment. Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
There is a human in the loop. If you have any questions, go for it. Whilst we're trying to update some of the code and deploy the site so it's available, so the new tools are available for you to play with, but all the previous stuff is out there. Go check it out, let me know what you think.
Okay, seriously, just imagine this. What if you could understand language, like directly from the electrical hum inside someone's brain?
Uh-huh.
Not words they speak, not text they type, but the actual thought captured just from electrical signals.
It sounds like science fiction, doesn't it?
Totally. But that's the incredible frontier we're diving into today.
And it's moving surprisingly fast from fiction to fact. We've got this stack of sources, research papers, articles, notes, all exploring this edge. Specifically, how AI models are learning to pick out language from, well, the really messy signals you get from EEG, electroencephalogram.
Right. So our mission here is to kind of cut through that complexity. We want to unpack the main challenge, look at the clever ways AI is being used, maybe celebrate some breakthroughs.
Yeah, and see where it's all heading.
Exactly. Think of this as, your short. Okay, seriously, just imagine this.
Issue with the website, so I have to discard that one later.
have you ever stopped to think about something kind of fascinating? I mean, uh, with every single move we make, our bodies are generating these tiny electrical signals.
Right, yeah, even just wiggling a finger.
Exactly.
They're-
From that tiny twitch to, walking down the street, it's all powered by these like invisible currents. Today, we're going to take a deep dive into that world, specifically electromyography, or EMG.
Mm-hmm.
And building on that idea, our deep dive today focuses on a really insightful bit of tech, the EMG hand simulation tool.
Ah, yes.
Yeah, and this isn't just like a picture. It's an interactive way for you to really explore that direct link between, say, making a fist or pointing and the electrical waveforms your muscles actually produce.
And that's a really key point, actually. Understanding what it's for is just as important as how it works.
Okay.
So our mission today basically is to unpack how this tool functions, what it's designed to teach you, and maybe just as important, what it's not meant for. And we'll touch on what's coming next for it, too.
And we've got some good stuff to work with. Our sources, they include detailed notes from development, technical descriptions. We even looked at some of the actual code behind it.
Oh, wow.
So yeah, we're getting a really granular view of how this simulation actually, comes alive for you, the user.
Good stuff. So maybe let's start with the basics. What is EMG?
Good idea.
So electromyography, it's essentially the process of capturing those electrical signals we talked about, the ones produced by your muscles when they contract.
Right.
Think of it like listening in on the electrical chatter of your muscles while they're busy working.
It's almost like hearing the body's hidden orchestra, isn't it?
Yeah.
I remember when I first really got that, it kind of changed how I thought about just moving.
Yeah, it's fundamental.
And the great thing about this tool is how it makes that concept real. So it simulates the electrical activity that you would record if you had electrodes placed near the hand muscles.
Right, if you were doing it for real.
Exactly. And what's really neat is how it visualizes these signals, these waveforms showing the muscle activity, and it does it in real time as you interact. That's really the core idea it's built on.
So that's the concept. But how does it actually work for someone using it?
Well, it's surprisingly straightforward.
Yeah.
You've got this hand diagram on the screen, right?
Mhm.
You just click on a finger. That simulates it moving. And when you do that, you see the finger twitch slightly on the screen, and bam, instantly, you see a corresponding jump in the recorded signals.
So it's immediate feedback.
Totally direct. A visual link between the action and the electrical result. And if you want to go faster, there are keyboard shortcuts, numbers 1 to 5 for the fingers. Plus, it works on touchscreens too.
And that real-time visualization is,
Yeah.
I think, what makes it so compelling.
Definitely.
As you click or tap, you see those EMG waveforms changing live, dynamically responding. Behind the scenes, the code's constantly updating the data, redrawing the signal paths on the graph.
Yeah.
It creates this really fluid, live picture of what's supposedly happening electrically.
What's also quite clever is how it adapts the display.
Oh, yeah. How so?
Well, depending on your screen width, it's not just about looking neat. It shows they really thought about the user experience, keeping it intuitive no matter the device.
Oh, okay.
So like on narrow screens, say a phone, the hand diagram sits above just one combined chart showing both electrode signals, saves space, keeps it all on one screen.
Makes sense.
But on a wider screen, like a desktop, the hand's on the left, and you get 2 separate charts for the electrodes, stacked vertically on the right. Gives you a more detailed view, uses the space better.
That is well thought out. And it has different modes, too, right, for learning?
Yeah, exactly. By default, it starts in demo mode.
Okay.
So the tool just automatically runs through simulating finger movements and showing the signals. Kind of lets you just watch and see how it works.
Right, passive learning.
And this is crucial if you decide to jump in yourself, click a finger, use a shortcut.
UK control.
Demo mode pauses automatically. Then you can switch between demo and user-controlled mode whenever you want. There's a button, or you can just press the D-Hema key. Lets you learn at your own speed.
Very flexible.
So we've covered how you interact, what you see, but that leads to the big question, right? We're not actually wired up. So how does it make these signals? How are they simulated? That seems like the real magic here.
Yeah, that is the interesting part, isn't it? How does it fake it so convincingly?
Uh-huh.
Well, when a finger gets activated in the simulation, the tool applies specific preset amplitude patterns. These simulate what the 2 virtual electrodes would be picking up.
Okay, amplitude patterns. What does that mean exactly?
So these simulated signals, they're generated by combining mathematical functions, things like sine waves, but then crucially mixing them with random noise.
Random noise. Why add noise?
Well, that's actually key to making it feel more real. Real biological signals are never perfectly smooth or predictable. They're messy.
Ah, right. There's always background interference.
Exactly. So adding that randomness, that noise, on top of a base signal makes the waveform look much more like something you'd actually record. It also subtly teaches you about the challenges of interpreting real EMG.
Gotcha. And you mentioned specific patterns.
Yes, they've defined specific amplitude values for each finger across the 2 simulated electrodes. For instance, activating the thumb gives electrode 1 an amplitude of 3, and electrode 2 gets 5.
Okay.
Index finger, that's 5 for electrode 1, 3 for electrode 2. Middle finger is balanced 4 and 4. Ring finger is 3 and 5, like the thumb, interestingly. And the pinky is 2 and 4.
Wow, that's really specific. So those different number combinations, like 3 and 5 versus 5 and 3, that's what makes the signal look different for each finger.
Precisely. These aren't just random numbers. They're designed to create distinct electrical signatures for each finger's movement. It helps illustrate the principle that different muscle activation patterns create unique EMG waveforms.
Okay, that makes sense. It really drives home that different movements produce different signals.
Right.
But this brings up a critical point you touched on earlier. This is not real medical data, right?
Absolutely not. And that's probably the most important takeaway here.
Okay.
The purpose of this detailed simulation, the patterns, the noise, it's all geared towards one thing: providing an intuitive, accessible introduction to the principles of EMG. It's purely for education.
Right. So for someone wanting to learn about EMG, this sounds fantastic. But we need to be crystal clear. You wouldn't use this for any kind of real-world research or, say, medical diagnosis.
Definitely not. It is not intended for diagnosing neuromuscular problems, guiding physical therapy, or anything like that. It's a simulator, a teaching aid. Think of it like a really sophisticated interactive textbook diagram, not a lab instrument.
That's a really important distinction to keep making. Educational tool, not diagnostic. Okay. So what about the future? Where does a tool like this go next?
Well, looking ahead, the developers have a clear vision. The focus is on keeping it simple, accessible, easy to use all on one screen.
Right.
And importantly, keeping it free from proprietary closed source stuff. Openness seems key.
Okay. Any new features planned?
Yeah, the really exciting part is they plan to incorporate other types of biomedical signals too.
Oh, like what?
Things like electroencephalograms, EEGs, brain activity signals, and electrocardiograms, ECGs, the heart's electrical signals.
Wow. Okay. So expanding beyond just muscles, that would broaden its educational reach quite a bit.
Massively. Imagine being able to interactively explore brain waves or heart rhythms in the same intuitive way.
That does sound powerful. Simulating brain activity, though, that must be way more complex than muscle signals, right? Are there unique challenges there?
Oh, undoubtedly. EEG signals are incredibly complex, influenced by so many factors. Simulating them meaningfully but simply will be a big challenge, but the potential payoff for learning is huge.
Yeah, I can see that. And you mentioned keeping it accessible. How are they managing that?
Well, on a practical note, the project welcomes feedback from users, and they also seek support through Patreon.
Crowdfunding.
Exactly. That support helps them enhance the features, improve the visuals, and crucially, maintain it as a free and open source resource for everyone.
That's great. Keeps it available for students, educators, anyone curious, really.
Precisely.
So let's kind of wrap this up. What we've seen in this deep dive is how a cleverly designed simulation can take something pretty complex, like EMG, and make it really accessible and, frankly, quite engaging for anyone. It turns these abstract scientific ideas into something you can actually play with and understand.
Yeah, it's a fantastic example of interactive learning.
Totally.
And maybe that leaves us with a final thought for you, the listener, to sort of chew on.
Okay.
Consider how tools like this, these interactive simulations, how could they change learning in other fields entirely? Imagine making quantum physics less abstract or complex economic models more tangible. It could really spark curiosity in ways we haven't even thought of yet, maybe fundamentally change how we learn new things.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to gently click like, subscribe, and comment. Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
Welcome to the deep dive. We take fascinating concepts, sort of strip away the jargon, and get straight to the impactful insights. Today, we're diving into something that, well, it underpins so much of our modern world. Think about how your phone processes signals, or even the rich sound of a symphony. We're talking about the Fourier series. Now, it's a powerful mathematical idea, and yeah, at first glance, it might seem pretty abstract. But we're going to explore how it becomes surprisingly tangible, almost, dare I say, intuitive, thanks to this really incredible interactive simulation we found.
And that's exactly why it's worth digging into, right? In a world just full of information, sometimes too much information, the Fourier series offers this really profound tool. It's about deconstructing what feels like overwhelming complexity into simple, understandable components. Gives you a clearer lens to view a very noisy world.
Exactly. So our mission today is to demystify some of that elegance. We're doing a deep dive into the Fourier series interactive simulation and explorer over at BioniChaos.com. Our goal really is to unravel how this brilliant tool takes a concept that can feel academic and makes it vibrantly real. It lets you visually grasp time domain signals, their frequency components, and these kind of mesmerizing visuals called epicycles.
Yes, the epicycles. That's essentially how you see those simple sine waves combining step by step to create the final signal. It's quite something.
It really is. Okay, so let's unpack this a bit. For those maybe familiar or needing a refresher, what exactly is the Fourier series at its core?
Well, the fundamental idea, the really profound assertion, is that any complex repeating signal, anything periodic, can be built, or you could say deconstructed, using just a combination of simple sine waves, nothing more.
Which is kind of mind-blowing when you first encounter it, that hidden order in things that seem chaotic. Right. And as you remember, each of those individual sine waves in the sum, it's defined by three key things. You've got its specific frequency, that's how quickly it wiggles, basically. Then its amplitude, how strong it is, its intensity, and finally, its phase, which is just its starting point in the cycle, its offset.
And what's really illuminating, I think, is how this seemingly straightforward idea can describe such immense complexity. The source material we looked at uses this great analogy. Think of the final intricate waveform, maybe a sound wave, as a finished dish.
Okay, like a recipe.
Exactly. The individual sine waves are the ingredients. Each ingredient has a specific amount that's its amplitude and a particular type that's its frequency. It's this surprisingly elegant recipe for constructing almost any repeating pattern you can imagine.
That's a great way to put it. And this interactive simulation from BioniChaos.com, well, that's what truly brings this concept to life. It doesn't just tell you about the theory, it actually lets you see it and even hear it happening.
Yeah, it's not just reading the recipe. You're watching the ingredients mix. You see the dish being prepared right there.
Which is just so powerful for learning, isn't it?
Oh, absolutely. When you're grappling with these, abstract mathematical ideas, visualization is often the fastest way to really get it. It cuts through a lot of the mental noise, helps you connect the dots much faster, which, let's face it, is key to absorbing a new knowledge without just feeling totally overwhelmed.
Definitely. So let's walk through it. How do you, the listener, use this simulation to explore these ideas? When you land on the BioniChaos.com page for this, you'll see a collection of presets right there on the left. These are pre-built signals you can just load instantly. You can select classic waveforms, things like the square wave, the sawtooth, the triangle, and it's genuinely, astonishing to watch how these sharp geometric shapes, with their sudden jumps,
Yeah, really abrupt change.
are built entirely from smooth, continuous sine waves.
Yeah.
That's the insight, right?
Yeah.
Even something seemingly unnatural like a square wave used in computing.
Is fundamentally just a symphony of smooth, natural sine waves added together.
It shows how things that seemed really different, like music and digital signals, are actually built from the same mathematical language. It's pretty cool. And beyond those classics, you can explore musical phenomena. There's beats, which is great. It visualizes the interference when you have two frequencies really close together. You see that wavering pattern.
And you can hear it too, that wah-wah sound.
Exactly. Or you can select three-tone chord and literally see and hear a simple musical chord being built from its parts. And if you want to see how richer sounds, richer timbres are formed, you can check out complex tone or 2 Hz plus 3 Hz. Shows more complex combinations. Now, the interactive controls are also really powerful. There's this drawing speed slider.
Ah, that's a key one.
It really is. It directly controls the passage of time in the simulation. So if you drag it slowly, you can really watch those rotating vectors. We'll get to those, build up the final shape bit by bit. Or if you just want to sit back, hit auto demo. It'll cycle through the waveforms for you, animating everything.
Kind of like a guided tour.
Right. But for that real aha moment, I think experimenting with the audio toggle is just incredibly illuminating. This lets you hear the signal you're seeing.
Yeah.
Each frequency component gets mapped to an audible pitch, and its amplitude determines the volume. It directly connects the math, the visual, to the sound we actually perceive.
That audio toggle, it really bridges the gap, doesn't it, between the abstract math and something, well, tangible, something you experience directly. It turns what could just be a visual exercise into something sensory. So thinking about that connection, what's maybe a surprising real-world thing that this clarifies for you?
Well, for me, it really drives home that when you listen to, say, a musical instrument, the richness or the timbre isn't some kind of, magical quality. It's literally just a specific blend of simple sine wave overtones stacked on top of the fundamental frequency.
The recipe again.
Exactly. Hearing a square wave being built, realizing how harsh and buzzy it sounds, yet knowing it's just made of smooth sines. It really makes you think.
How often do we hear complex sounds without realizing they're just these combinations of simple underlying waves?
Precisely. It's like hearing the recipe come to life. Okay, now let's dive into the core of how this tool creates those moments, those insights. It's got these 3 interconnected panes, right?
Yes, 3 main windows or views.
And each gives you a different perspective, but they all work together, showing the same information, just differently.
Precisely, yeah.
So at the top, you've got the big one, the time domain pane. This is probably the view most people are familiar with. It just plots the signal's final amplitude, its strength, up and down against time, moving left to right. And there's a little white dot that traces the signal's value as it's being generated. Standard waveform view, basically.
Pretty straightforward.
Then below that, bottom left, is the epicycles pane. Now this, for me anyway, is the real heart of the simulation.
I agree. That's where the magic happens visually.
It is. You see the Fourier series dynamically at work.
Yeah.
What you're looking at is a series of rotating arrows. The term is phasors.
Right, like little spinning clock hands.
Kind of, and they're chained together head to tail, starting from a center point. Each one of those arrows represents a single sine wave component from the recipe. Its length tells you its amplitude, how strong that component is.
Longer arrow, louder component.
Exactly. And its speed of rotation tells you its frequency. Faster spin, higher pitch.
Makes sense.
And the truly cool part is how the tip of the very last phasor in the chain traces out the entire waveform in real time. What it draws perfectly matches the graph in the time domain pane above it.
It visually performs the addition of all those rotating sine waves.
Yep. And then finally, bottom right, you have the frequency domain pane. Think of this as the static view, the signal's recipe card, or its spectrum.
The list of ingredients.
The perfect analogy. The horizontal axis here is frequency low to high. The vertical axis is amplitude weak to strong. Each bar you see standing up in this pane represents one single sine wave component needed to build the signal.
And the taller the bar.
The more that specific frequency contributes, the stronger that ingredient is in the final mix.
So if we really connect these 3, they're not just separate displays. As you said, they are this unified dynamic system. It's quite elegant. The frequency domain gives you that list. Frequencies, amplitudes, static.
The recipe.
The recipe. Then the epicycles pane takes that recipe and brings it to life. It dynamically sums those components as rotating vectors. You see the process of creation.
You watch the dish being made.
Exactly. And then the vertical position and the final point in that epicycle chain, when you plot that over time, well, that creates the exact graph you see in the time domain.
Boom. The finished waveform.
It's a complete circle. From ingredients to mixing to the final result, it really offers this profound sense of clarity about how it all works together.
It's just an incredibly clever piece of visualization.
Yeah.
And it's exciting that it's apparently an ongoing project. The creators mentioned possible future updates that could, deepen the understanding even more.
Oh, like what?
Well, imagine being able to just draw your own custom waveform right on the screen.
Wow.
And then have the simulation instantly compute its Fourier series, show you the epicycles and the frequency spectrum for your drawing.
That would be fantastic. A real sandbox.
Totally. And they're also thinking about more advanced controls, letting you tweak phase, amplitude, frequency directly, plus maybe adding more educational content, even the math derivations for those who want to go deeper.
Yeah. Those features, especially the drawing part, hold immense potential. Being able to directly manipulate things and instantly see the graphical and the audible results, that would turn it into an even more powerful interactive lab for just exploring and discovery.
For sure. So wrapping things up, we've taken a deep dive today into the Fourier series. We've revisited how this fundamental mathematical idea Lets us deconstruct really complex signals, sounds, images, electrical currents, whatever, into their basic, simple sine wave part.
They're building blocks.
They're building blocks, exactly. And crucially, we've seen how this simulation from BioniChaos.com makes that whole abstract idea incredible, accessible, visual, and even audible. We hope this deep dive has maybe offered some new perspectives or perhaps strengthened your understanding of this really fascinating and fundamental concept.
And maybe, just to leave you with a final thought to mull over, consider how many other seemingly complex things in our world, maybe beyond just sound or signals, might also be broken down into simpler fundamental components. If only we had the right lens or the right recipe to view them through. This kind of thinking, breaking down complexity into its building blocks, it's a powerful tool that you can apply in so many areas, really.
That's a great point. It really makes you wonder about the hidden recipes everywhere, doesn't it?
Yeah.
We definitely encourage you. Head over to BioniChaos.com, find the Fourier series simulation, and just play with it. Explore it for yourselves. See what connections you make, what insights click for you. Until next time on The Deep Dive.